So this talk can be a little bit different than we've had so far. I typically, is there anybody in the room who's used MKL-DNN directly? This is typically the response we get. So I'm not going to get into actual API syntax, and I'm not going to get into performance numbers. What I'm going to do is tell you what the library does, what it's for, and give some overview concepts, because we've been told that it's hard to learn. The uptake's pretty tough. So the idea, hopefully, is that I can give you some overview concepts, and whenever you get around to using it, that'll color the way you sort of look at the library, and it'll be a little bit easier to use. And then you can look back at this whole entire slide presentation when that time comes. I hope it'll help you out. So before we get started, I want to orient everybody into in space of what we're talking about here, right? So tomorrow, this AI stack will be, the whole top of this will be talked about in my Python talk. This is probably what most of the users are used to dealing with and integrating with. TensorFlow, PyTorch, these kind of things. But the entire stack from Intel, of course, includes the processor, the math libraries underneath, and then the frameworks on top. Today we're going to talk about this piece right here, MKL-DNN. I guess I should say that it's open source. If anybody wants to contribute, we'd love to hear from you. That also means that we have a pretty healthy environment on GitHub. If you have questions and you submit them to our GitHub, the actual engineering team monitors it every day, and some of the best people on the team are pushed to give their thoughts and comments on there. You'll get direct support and help from the actual engineers from the team. So MKL has multiple groups of functions within it, and one of them used to be deep neural networks, right? And that was maybe 2 years ago. It was pulled out of MKL and made its own library called MKL-DNN. And at that time, most of it was still just relying on MKL code and basically putting a new API on top of it. Over time, they've pulled themselves farther and farther away. As of now, there's maybe 1 or 2 MKL calls in the entire MKL-DNN library. And if you fast forward 3 or 4 months from now, there'll be 0 relation at all. The deep learning portion of MKL, the left side, is deprecated. I think it's gone in the next version. I think in 2020 Gold, it's completely out of the library. So there'll be 2 separate libraries. The naming will be a little bit unfortunate to confuse everybody. But MKL-DNN will not have anything to do with MKL fairly soon. So again, trying to orient you in space. If you've seen our talks for the Python analytics or for TensorFlow, you've probably seen these kind of instructions. This is how you get our Python. This is how you get our TensorFlow, and you want to get it with MKL support. You'll see that all the time, right? So what I'm covering today is what that MKL support is. So it's actually MKL-DNN. But when you see these kind of instructions, this is the math you're getting underneath, basically. It's important to start with what the library is and what it's not. So everything in the green square is what MKL-DNN does, right? What it does not do are things like final predictions in an inference chain, right? It does not calculate a loss function for you. It does not update the weights. Right? So it doesn't do any of that stuff. It just does these compute-intensive operations. Whatever you need to do in your deep neural network that's tough, needs to be done fast, they have small little primitives that they build to do those things. You have to write all the orchestration code yourself. So all these arrows, you're writing that code yourself, right? So this is for framework developers. This is for the guys and gals working on TensorFlow directly to make it faster for you. This is not for people in the abstract space trying to solve a problem with TensorFlow. This is not who the library is targeted at. Targeted for the people trying to make TensorFlow faster. This is the primitive coverage. If you want to read them off, you can. But just the idea is maybe convolution is what we'll write fast, not how to use the convolution. Inner product, activations, reorders, those kind of things. So the take-home message here is it's compiler independent, it's OS agnostic, it's open source, these kind of things. It's already been put underneath these frameworks. So we have internal teams working on most of these and external contributors. So if you want to work in the framework space, you can maybe ignore most of this talk. But this will kind of give you an idea what's underneath. There's currently int8 support for inference, but only float32 for training. We're working on adding more int8 support. And of course, it's optimized for Intel processors. So the whole idea of the project is we understand the processor better than anybody else, and we need to write code close to the processor as possible to make our deep learning faster. Does it support mixed precision? Yes. Yeah, so there's a version 1.0 that's in beta right now that I believe we are going to convert to officially a gold type release maybe 6 or 7 weeks from now, and there will be BF16 support in that release. Yeah, it's tricky because it's only in beta. I'm not supposed to really present it, but you can get it right now. There's an RC out on GitHub that you can just get and use. It's called 1.0, whereas everything else has been called 0.1, 0.18, those kind of things, 1.9, or 0.19. But if you see 1.0 on GitHub, that's the new version of the library. How does it support it? Yes, so there's threaded code written for you in the library. You're not addressing it with your code. You're not writing OpenMP calls. When you call the primitives, anyways, but they're threading underneath. Yeah. So the TensorFlow team, they will write in the Python layer, and their goal is to take what you've put into your session for TensorFlow, and they try to map it to MKL-DNN primitives. Right? So their job is to, if you pass an LCM topology, their job is to identify which primitives are in that topology, and then they call MKL-DNN for you. So there should be no difference in the way you use it, but you do have to call it different. I mean, it has a different name. It's a different, it's a different primitive. Yeah. So it just works with the global idea of setting OpenMP threads. OMP underscore num underscore threads. And then it just runs with whatever you tell it there. Yeah. So like I said, this is going to be a little different. I want to go over overview concepts. So if you actually try to sit down and use this library, it will be less scary. If you see these concepts first, I promise it's not as bad as it looks. We'll talk about philosophy first. There are multiple structures in the library, but there's 3 main ones, right? And these 3 main ones are all you should think of when you look at MKL-DNN. First one is a descriptor. This is lightweight. It describes what the memory will look like, what the primitive should look like downstream. But it doesn't know anything about the execution context of the engine, right? Then there's a primitive, which is the actual piece of math that will run. And this, of course, has to understand what the execution environment is. So if it's running a CPU or GPU, that all has to be incorporated into the primitive itself. So it's a little bit less lightweight, right? And then memory, of course. So memory is a handle to data. They actually call it a memory. That's the name of the primitive. And so the goal is to load up data into memory, pass it to a primitive, put that primitive into a stream, which is the actual execution context, and then push everything in the stream in order. So this is the stream, primitives in the stream, input memory, output memory. Right? Pretty straightforward. And I put the whole engine box in red because this engine could be CPU or GPU, and then we'll add accelerators in the future. A little bit more in-depth version of the same image. Everything on top of the red line, so everything on top of here is engine agnostic, right? So this kind of stuff, it doesn't matter where you're running it. And these are the descriptors that you start with. So it's important to, when you actually sit down and use a library, because you'll hear things like memory descriptor, memory primitive descriptor, memory, operation descriptor, and it starts getting confusing. It's like spaghetti, right? Just word spaghetti everywhere. Start with descriptors. Then go down to the actual primitives. These primitives require you to understand what the engine is and how it's going to run. So that's why everything above is engine agnostic and everything below is engine aware. Set up what you want to do, tell MKL-DNN what the engine is, and then that creates your primitives. I have these weird-looking rectangles here because we want to run in a special MKL-DNN format that I'll talk about later. So your input memory probably comes in something like NCHW, whatever you're used to using in a neural network, but it's going to run on the CPU in a special blocked format that we call it. So it's very important to try to get as many primitives as you can chained together working on our blocked format. And we have a way to tell you what our block format is recommended for your given execution. But you want to think of it as you come in, you bring in your own memory, your own data, let us reorder it for you, and then pass it through a ton of primitives, as many as you can possibly get chained together while in our memory format, and then I'll go back to user memory in the end. Next, I'm going to cover what's inside each object. So this, as I mentioned, you want to stay inside our memory format and chain together a bunch of primitives, right? So I'm going to talk about what attributes are in each object, and hopefully this will show you that it's fairly easy. It's an easy concept to understand and use. You start with a memory descriptor. This has things like, I told you, it's a lightweight. It just tells MKL-DNN what you want to do downstream. It's not engine aware yet, so it has dimensions, data format, data type, those kind of things, right? Then you create an actual primitive itself of memory, and this is engine aware. So of course, an input has to be the engine. Pretty straightforward, right? And the data handle is a pointer. The important thing to note when I say things like we need to understand what memory format we're in, we want to get to MKL-DNN's recommended memory format, and then stay in that format through the entire execution, we have queries built in. So this memory has a .get descriptor, which will return what format that's in. It'll return things like what the data type was, what the data format is, what the dimensions are. So you can tell primitives, when you get to the primitive side, what that memory was just by passing that query. And on the descriptor side, you start with an operation descriptor, then operation primitive descriptor, and then a primitive. So again, the words get confusing. It's unfortunate, but it's the way it is. So all the inputs are here, lightweight, then you add the engine, then you create the actual primitive. Then you would pass it to the stream, and you would file through as many as you can, right? Again, there's descriptors here. So this is where the descriptors become very important in the queries. So if you have an operation, let's say convolution, and then you have a ReLU afterwards, right? Convolution is extremely compute intensive. So you need to let MKL-DNN tell you what your format should be going into that convolution, and just take whatever MKL-DNN says. The next one, the ReLU, is not compute intensive. So you want the ReLU to just run off whatever the output from the convolution was. So when you create your ReLU primitive, you would take the destination descriptor, the DST descriptor from the convolution, and pass that as an argument to the ReLU input. So you're just telling the ReLU to run on whatever format the convolution output. These are all done with these queries, these built-in queries. Of course, performance is the main goal of this library, so there's a few things we want to impart on you before you use it, send you down the right path. Memory layouts are extremely important. Unfortunately, CPUs are not strong on the popular NH channels first, channels last formats. As I mentioned earlier, we have our own versions, we have our own blocked layouts that are lay out memory in such a way that the access during a given primitive is optimized. So the idea is you have input data and you want to convert it to ours. We provide reorders to do that for you. So just like there's a memory, there's an operation primitive, there's also a reorder primitive. So if you ask MKL-DNN when you create a convolution, what do you want the format to be? It's going to give you an answer. Then you can load up a reorder primitive and say, take what the convolution told me it wants and convert your data, and we'll do all that for you in what's called a reorder primitive. If you're in the framework space, it's not so important to you because you don't have to deal with it, but you just know it's happening underneath. So the framework teams are constantly checking each compute-intensive primitive and asking MKL-DNN what the format should be. When I showed the primitive block layout, the idea was to stay in the format that MKL-DNN recommends for as many primitives as possible. And that's propagation of layouts, what we call that. So when you sit down to use it, this slide should be very helpful because these are the steps you need to do to follow the propagation. But the idea is create a memory descriptor. and then create a primitive and any descriptors you need in the order there, right? And then create reorders. So the idea is create reorders everywhere and just do a conditional, right? So you create reorder for every single compute-intensive operation, and then you tell MKL-DNN, you write conditionals in your C++ code, but if it doesn't match what MKL-DNN asked for, then reorder it. So that's the easiest way to do it, so that it always, the conditionals only fire when needed. If not, they don't fire. And then push all the primitives and the reorders before each one to the stream, and then hit go. So that's the way you would actually do it if you sit down. Hopefully this slide will be helpful if anybody sits down to try it. Another performance consideration is fusing computations, right? So there's a few compute-intensive operations in the deep neural network: convolution, batch norm, and inner product. Everything else is mainly bandwidth limited. So instead of calling convolution and then calling a ReLU, what MKL-DNN says is we know that a lot of times you'll do a ReLU right after a convolution. We have a fused version of the primitive that has one basically memory pool, and then we run both of the operations. So instead of loading up two primitives, you load up a single one that's a fused version of these common operations. That's what this is showing here. So instead of convolution sum ReLU, we just have one fused. Downside is we add them responsively. So we see that a lot of users are using the same primitives back to back to back, so we add a fused version of that. But then you have to get a list of which ones are fused. So in order to use these, you kind of have to go to the documentation and find which ones are available. There's not a good scalable solution to that yet. This is a little bit outdated. It says Caffe already supports this. I know the TensorFlow team has a ton of these already integrated, and the PyTorch team's the same way. So if you're using TensorFlow and PyTorch, you're getting these fused operations. If you're using MKL-DNN directly, since it's inference, you already have a model. So you should not think of this as training in int8. You build a model, you have a model that's ready to go. Then on the inference side, you quantize the model itself, and then you pass data through it. So there's not really much to go over other than we have the support for it. That's probably the best thing to say. Then more nuts and bolts. This will be very helpful, I think, if you actually sit down and use the library. The way we do fusing and the way we do quantized models are through attributes. But like I said, we know that you use ReLU after convolution, so we give you a fused version of convolution ReLU. That's not really true. What we do is give you a post-op attribute to the convolution that you put a ReLU in, right? So you build a convolution, you add an attribute to it called a post-op, and that post-op is defined as a ReLU. So you don't really have any ReLU primitive anywhere. That's the post-ops. Quantized models are the same way. So there's an attribute called something like set quantize or set int, something like that. And it's added to the primitive itself. This is the most important slide in the whole talk. A lot of times people will say, this is great, I have this code, and I think I can get a fast, CPU primitive out of MKL-DNN. Then they jump into the library, they'll do a convolution, and then they'll go back into their native layer of the Python. So you have to do a reorder in for a block layout, and then you have to do a reorder out. Right? So if you come in and out of the library, you're not going to get a good benefit, because you're going to pay a price for every reorder. So the longer you stay in, the more you propagate your layout, the more benefit you get from the library. And of course, if you use our fused primitives, if you buy into the library completely and use our fused primitives, then you get even a better benefit, right? So the idea is that the more integration, the more benefit. This naive integration is almost not worth it most of the time. How to get it? There's not, let's just say we don't have well-defined binaries yet in how we want to distribute them, so I can't provide the data science team with good working version. We usually ask everybody to build it from source. Because of that, we have a nice walkthrough that just holds your hand through the entire process. There should be no troubleshooting. Go to the walkthrough. You can find it on the MKL-DNN GitHub page. The main README has a few links, and one of them's called like installation and walkthrough, something like that. If you go there, you can follow all the steps. There's never any problems, except for maybe on Windows, but not on Linux. We have a full validation suite in there too. You just say make tests, and then it validates it for you. You'll do a bunch of tests, and it'll tell you what percentage of them passed. It should be 100%, but if not, it tells you which ones failed, and then you go to our GitHub page and you send a question and say, this is my environment. Test number 45 and test number 67 failed. Do you have any ideas? And then we'll help you with it. If you're working on the framework side, a lot of times we get asked, how do I know MKL-DNN is working? All right, so maybe in your situation, data science team tells you if you load up this PyTorch from this location, it has Intel's optimizations in it, and you want to test Corey's work back there, make sure that he's telling you the truth. The way to do it is export this environment variable, verbose equals 1, and call your program. If verbose is set to 1, MKL-DNN will just print a nice trace of every operation that it runs. If you don't see any MKL-DNN calls, let's say in ResNet 50 in your TensorFlow side, then you don't have MKL. Right? That's pretty straightforward. This verbose trace, if you're using the library directly, it's better. It's more than just showing you the MKL-DNN running. You actually get some information out of it, right? So it'll say things like, what was the name of the primitive? Was it a reorder? Is it, let's say, convolution, these kind of things. When we JIT it, what do we target? So do we target AVX2? Do we target AVX512? You can use that to sort of diagnose whether you are getting what you expect based on your hardware. It'll say things like, what was the data format? It's the block format here, right? And if there was any sort of post-op, it'll say post-op attribute used, these kind of things. And then it gives time spent in each primitive. And you can use this a lot of times if you've, let's say, you haven't done well with your format propagation, and every single primitive does another reorder before it, and you're very slow at performance. You would see reorder primitive, reorder primitive, reorder primitive, reorder primitive. And the trace will really help you to sort of diagnose propagation issues. I'm not going to get into the TensorFlow stuff because that's next time. That's the Python talk. But I do want to show you sort of when you see these kind of things tomorrow. Yeah, this kind of stuff. This is just talking about how MKL-DNN is put inside TensorFlow. So when I get into that talk tomorrow, hopefully you can connect the two. That's what we're talking about. Questions? The operation coverage and the order of us adding stuff to the library is basically responsive to them, but the API calls are not. We have some each one of the framework teams has written their own little basically text parser, right, for this, but we don't have an official one supported by the library. If you're using it directly and you want something like that, I mean, especially somebody that coming from a workshop like this or from Argonne, complain to us, because that gives me ammunition to go to the dev team and say, this is important. But right now we don't have an official one. I can tell you every single framework team writes their own, though, because it's when you have thousands of lines of a trace, it's useless if you have to read it. I'll plug an article that I wrote maybe a month ago in the Python talk. It's called something like performance considerations for TensorFlow, something like that. But it's on the Intel website, so if you type in performance considerations TensorFlow, my last name, come up. And it says it's for TensorFlow, but all the settings are basically MKL-DNN settings. So if you read that article and you get down to the MKL-DNN stuff, it talks about what runtime settings are important, a description of why they're important, and then gives you a recommended setting for MKL-DNN. I'll show that article in the talk tomorrow if you want to get the actual link to it. But that has all our recommendations, the ones that matter.